There you are again. This is our third session. I go back and forth between calling this Logic 3 and Logic 2B, just because it has something of a supplementary flavor rather than really a substantive sense. That is, we're not covering a lot of, or even much at all, new material in this session. The point today is to bring together everything we've done so far. Everything we've done so far includes the elementary elements of the elementary topics in propositional or truth functional or sentential logic. We're bringing that to an end. Reflect a little bit on what logic can do, can't do, as evinced by what it can do in its propositional truth functional form. Then we're going to move on to other modes of inference, rounding out the first half of this semester, and then go on to predicate logic. I want to take this opportunity to remind everyone that for the kind of logic we are talking about, and here I would distinguish it sharply from any advanced type of logic, any course, for example, that we would offer in the spring semester, any course in philosophical logic. In this kind of logic, we are always concerned to master two skills simultaneously. There is the skill of manipulating the symbolic language, demonstrating the validity or invalidity of arguments, for example, so inferential rules, rules of equivalence, truth tables at the most elementary. But we are also always engaged this semester in moving back and forth between natural language and the symbolic language. This is not a concern once you advance to philosophical logic. With philosophical logic, we soon give up the idea that a complex logical formula reflects some ordinary kind of statement in a natural language, okay? But in this semester of logic, the ability to move back and forth is always essential to what we're doing. That's why in this form of logic, both truth functional logic in the first half of this semester, predicate logic in the second half, in this form of logic, we can always think of what we're doing as formalizing what we would be doing anyway. That act of formalization and the act of translation reach their peak, you might say, near the end of this semester, when we look at a philosophical analysis of the word the. And so we learn how to render phrases beginning with the into logical language, okay? That's always a concern, moving between natural form and logical form. When I teach logic, when I have taught logic to undergraduates, it has been my experience that they have more trouble than the typical graduate student in moving back and forth between natural language and logical language. And for that reason, well, one of the differences between this course and an undergraduate course is that in an undergraduate course, I tend to teach and stick with a single mode of argument testing, single proof method. We do not, for example, use rules of inference or conditional proof in the undergraduate course. We go directly to truth trees because they are an elegant and straightforward truth method, and that liberates more classroom time to spend on the act of translation. In my experience, graduate students do not have anywhere near that same kind of difficulty moving back and forth between the natural language and the symbolic language, and therefore we have more time to explore and become proficient in a variety of truth methods, proof methods. I still want to wrap up propositional logic's first phase today with some general observations about translation, and then we're going to get into some review cases of using truth tables to test the validity of an argument, truth tables whether full or partial, and then the concept of implication, mutual implication, and equivalence. That's what we're going to cover today. So first with translation, I'm not going to go through the connectives in their canonical sense. I just want to make a few observations about some of them and how they're used. To some degree, this will repeat what we did in previous lectures, but only to some degree. With the word not, and this, by the way, W.V. Quine always took great pains to emphasize when explaining the concept of negation. With the word not and with the connective that we call negation, you want to be sure you're not just inserting the word not into any old sentence in any old place and thereby achieving the negation of the sentence. You may not. In a simple example, there's no ambiguity, not much room for error. 5 is a prime number. Let's call that statement F, and we negate it, not F. Not F then could be stated, it's not the case that 5 is a prime number, or it's not true that 5 is a prime number, or most simply, 5 is not a prime number. There's no confusion there. If 5 is not a prime number, it's a number that is equally divisible by some number other than itself or the number 1. So there we have no ambiguity, no opportunity for misunderstanding. But now suppose we look at a patently false sentence. Vienna is a prime number. Nonsense, you say. Sure. But we negate that. So that statement V is clearly false. You all know it's false. When we negate it, the negation of V must be, always is true. Why? Because in the language of logic, unlike the language of ordinary speech and writing, every statement has a truth value. If the truth value is not T, true, then it's F, false. Okay, so Vienna is a prime number. Nonsense, you say. We want to negate that. But we do not want to say Vienna is not a prime number, where that might lead someone even to conclude that Vienna is a non-prime. You know, you can divide it by some other number other than itself or 1. Okay. You don't want to permit that kind of ambiguity because Vienna is a non-prime is just as false as Vienna is a prime. You don't even need nonsense sentences to make an example like that. Suppose the statement is, I'm happy, and you want to negate that. Don't say I'm unhappy, because of course there are other possibilities besides being happy or unhappy. One might be just lolling about in a state of indifference between the two. Okay? So you'd have to say, it's not the case that I am happy, or I am not happy, or it's not true that I am happy. With certain kinds of statements, and especially when we start speaking of everyone, everything, all the time, you have to be careful in a different way when negating. Everyone on the starting lineup got on base. That's a description of an inning in baseball, of course. Everyone on the starting lineup got on base. And if you negate that, some people might say, people even say ordinarily in conversation, everyone on the starting lineup did not get on base. But that's ambiguous. It's ambiguous between the statement, it's not true that everyone on the starting lineup got on base, and the statement that everyone on the starting lineup failed to get on base. All right. So here we have an ambiguity because it is complex and confusing when you use everyone and not. Well, in general, human beings find it harder to process negations. That's why so often you've maybe tried this trick on someone or had it tried on you. You say to someone, what's the opposite of not in? And they say out. Okay. And then you get to tell them, no, the opposite of not in, of course, is in, right? But negations just don't get processed in quite the smooth, quick way that other connectives do. So this is just a word of warning. And again, in that beautiful, that lovable old song, Home on the Range, there's an example of a negation statement that can be hard to process. The skies are not cloudy all day. Well, which one is it? Is this making the grand, very appealing, but almost certainly false statement that the skies are cloudless all day? Or is it making the much truer, safer, but also less enticing claim that it's not the case that the skies are completely cloudy all day long? Okay, that's just an example of how negation can be hard to process in natural language, and we need to take extra care when processing negations in the translation between natural language and logical language. Now a few words about the material conditional, the if-then, and its closely related concept, only if. Here we want to distinguish between necessary conditions and sufficient conditions. If A, then B. And incidentally, always remember that this A horseshoe B may be read if A, then B, and may equally be read at any time as A only if B. Same thing, A only if B. If A, then B. If A, then B asserts that A is a sufficient condition for B, maybe a false claim, but that's what the claim is. A is a sufficient condition for B. B, meanwhile, is a necessary condition for A. That's why we can read this A only if B. If we hung up a bird feeder, we'll hear the birds singing. If we hung up a bird feeder, we'll hear the birds singing. That is to say, the hanging up of the bird feeder is a sufficient condition for hearing the birds singing. That's what that sentence asserts. The hearing of the birds singing is a necessary condition for having hung up the bird feeder. So as a loose equivalent to if we hung up a bird feeder, we'll hear the birds singing, we might say we hung up a bird feeder only if we hear the birds singing. You think like, did Nick remember to hang up the bird feeder? And then there's the twittering of birds. You say, right? And given I know that the hearing of the birds is necessary, right? So we must have hung up the bird feeder. The sound of the bird song is a necessary condition for determining whether or not the bird feeder was hung up. It does not follow, by the way, that the hanging of the bird feeder is a necessary condition for the singing of the birds. You might hear them singing for another reason. So actually, I misstated something just a second ago. It's not that if I hear the birds singing, therefore the bird feeder was hung up. My apologies. To say that the sound of the bird singing is a necessary condition is rather to say that if I fail to hear the birds singing, right, if I fail to hear the birds singing, then I know the bird feeder was not hung up. Sorry about that. The very fact that I could slip into that error shows how easy such errors are to slip into. Now, the word only in a conditional statement very often signals that a necessary condition is being asserted. But because the word only can move around in a sentence, we sometimes have to think a little extra clearly to figure out where the word only belongs. Let's just define the two elementary propositions in this conditional. O and S. O, the sun is very old. S, the sun will supernova. So here we're saying the sun will only supernova if it's very old. That is, the extreme old age of the sun is a necessary condition for its supernovaing. It will not supernova unless it's very old. It's got to be very old. Whatever else has to be the case, it also has to be very old before it supernovas. Okay. So this is not saying if the sun is very old, then it will supernova. Okay. It's saying the sun will supernova only if it's very old. This only is a little bit confusing because it appears in the middle of another proposition, but it really goes with that if, okay? So it's not if O then S, it's if S then O. If the sun supernovas, then it's very old. Or the sun will supernova only if it's very old. How do you know that that's the right meaning to only? Well, to some degree, we always fall back on logical intuitions, grammatical intuitions. To state something that I'm sure you all have no difficulty with, there are other equivalents to if then in ordinary language, like provided. We're walking provided that our shoes are dry. That is, if our shoes are dry, we'll walk. Sometimes you don't even have a conjunction and you have to figure out that there's a conditional being stated. He sees his shadow, so we'll have 6 more weeks of winter, right? That is to say, if he sees his shadow, then we have 6 more weeks of winter. Finally, let me just return to something I touched on quickly the last time, unless. But to show what's going on with unless, we can work a first example of a truth table for today. You all recall vividly that the material conditional is false only one time. That is, it's false only when the antecedent is true and the consequent is false. Now, I think you can quickly see how we can produce a column of truth values for not P or Q. Not P, of course, is just the negation of P here. When will not P or Q be false? It'll only be false when not P is false and when Q is also false. That's in the second line. Otherwise, this disjunction is true. And you can work through this yourselves at home if you want to double check. Well, you can see that the column for if P then Q is identical to the column for not P or Q. That's one way of saying, and this is a point that's going to matter when we look at the meta logic of propositional logic. It's another way of saying that you don't really have to have a material conditional in order to say everything that can be said in logic. You can really get by with less than that. Okay. If P then Q is the same as not P or Q. I'm bringing this up now for the following reason. Suppose I have a sentence, I drink soda unless it's Friday. Unless today is Friday. What is a sentence like that asserting? Well, what does, I once raised this question in class and a student looked at me and said, I'm not sure what unless means. Okay, what does unless mean? When do I use an assertion like this? I drink soda unless today is Friday. I'm asserting that if today is not Friday, I drink soda. Something can, in fact, stand in the way of my drinking soda. It would be the fact of today's being Friday. So if we're gonna use S for drink soda, F for today is Friday, and I'm saying if today is not Friday, I'll be drinking soda today. You can be sure of it. If today is not Friday, then I'll drink soda. But we just saw, and we just demonstrated using the truth table, that this assertion is equivalent to the negation of the antecedent or the consequent. But the negation of a negation is just the assertion, F or S, same thing, S or F, because as you recall, disjunction is commutative, unlike the conditional. Disjunction and conjunction are commutative. So I drink soda. Today is Friday. And the more interesting looking conjunction unless turns out to have the same logical value and sense as the familiar disjunction or. Now let's put ourselves inside the language of logic, inside the symbolisms of it, and just try to do some examples with truth tables so that we're all familiar with what truth tables do and how they do it. A first example I just want to look at quickly involves the truth table elucidation of a formula that uses parentheses. Once you have parentheses in a formula, it's a safe bet that you're going to have to figure out a truth value of some part of the formula before you go on to the whole formula. So let's look at two statements that might look very similar to one another. If I am at least 18 years old and I am a citizen, then I can vote. The second sentence says, I am at least 18 years old, and if I am a citizen, then I can vote. Well, intuitively, you can see a difference between these two, because the first one is entirely a conditional. It states the necessary conditions, the conditions for the right to vote. The second one, while it covers the same factual ground, as you might say, also contains an assertion that the other one did not. It contains the assertion that I am at least 18 years old. So E for 18, as in I'm 18. So here, I'm at least 18 years old and I'm a citizen, then I can vote. And this one says E, and if C, then V, C horseshoe V. How are these two assertions related to one another? Well, I just made the comment that they're not identical. You can see that. You don't need any of that fancy logic to show you that they're not identical. One of them is asserting I'm at least 18 years old. The other one is not asserting it. Fine. But again, we can see that intuitively. Let's see it logically. We've got 3 propositions in this truth table. That means we'll have 8 rows. But you notice I made a couple of extra columns. I made a few extra columns because where you have a longer statement that contains a parenthetical statement inside it, okay, where that's the case, it's best, until you acquire considerable facility with working out truth tables, it's best to have a separate column for that part of the complete proposition, okay, so that you can piece together the truth value. If you do truth tables by hand, incidentally, this is just one example of why you want to use a lined sheet of paper so that the rows don't get confused. better still, type out what you're doing. All right then. What's the conjunction of E and C? Well, you know down here, E is false, so that part's easy. And here, C is false. All right, so there's that. By the way, that simplifies things because, right, remember that when the antecedent to a conditional statement is false, when the antecedent is false, the conditional as a whole is true. You just saw that only the first two rows have a true antecedent. So we're only going to have to look at the consequence of that conditional in those two rows. In the next 6, you know already that the conditional is going to be true, right? When you've got a false antecedent, the conditional as a whole is true. Okay, so here the antecedent is true, and what's V? Okay, true in one case, false in the other, so too the truth value of the whole thing. Okay, so this one statement, if I'm at least 18 years old and I'm a citizen, then I can vote. Only turns out to be false in one instance. Okay. Now, let's do the same thing and build the column for E and if C then V. If C then V, let's see, it's going to be true, false, true, 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 false, true, true. Okay. And then we want to take the conjunction of that with E. Well, E is false down here. So this statement is true in 3 places and otherwise false. This statement is true in 7 places and only false once. Are the 2 statements equivalent? They are obviously not equivalent. Even one discrepancy between the 2 columns of truth values shows you that they are not asserting the same thing. But now we can ask a different question. We can ask a separate question. We may ask, does one of them imply the other? Is it possible that they both imply one another? Could they both imply one another? No. You know this already because they're not equivalent. When 2 statements imply one another, they're equivalent. When they're equivalent, they have identical columns on the truth tables. Therefore, if they're not equivalent, they're not going to both imply one another. Is it possible that neither of the statements implies the other? Sure, that happens all the time. 2 statements may have nothing at all to do with one another. But it's also possible when you've got 2 statements that one of them implies the other. How would you tell? Again, we're looking at this statement and this statement. Is it possible for E and C to imply is it possible for if E and C then V to imply E and if C then V? Well, that would depend on whether there's a single line of the truth table in which the premise is true, but the conclusion is false. True premise, false, false, true, 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 true. But wait, we've got here a true premise, false conclusion. And again, and again and again. So this does not imply this. What about in the opposite direction? Here, in all three of the rows in which the premise is true, that is, if the premise is I am 18 and if I'm a citizen, then I can vote. In each row that is true, we find that the conclusion of that little argument is likewise true. So the statement, I'm 18, I'm at least 18, and if I'm a citizen, then I can vote, does imply the statement, if I am at least 18 and I'm a citizen, then I can vote. Okay. So that's a quick look at implication, equivalence, and the manipulation of the truth table, the full truth table. We can always do more extensive examples. The full truth table lends itself to any number of examples, but as you know, and as we've observed, both publicly and I would guess privately, it's an awfully tedious method. We want to use at least one. We want to be comfortable with at least one of the alternatives to the full truth table. That is either the partial truth table or the short truth table. I guess I've already made clear that I prefer the partial truth table. Maybe I did say one reason was you don't have to improvise, you don't have to figure out your approach. Another way of putting the same reason is, even though the partial truth table is a lot less work, it's very clear how you write out your work when you're doing the partial truth table. Here's an argument that uses 3 elementary propositions, and therefore, of course, is going to have a truth table consisting of 8 lines. So, if not A, then B, then C. If C, then A and C. B, well, we can just have B as a premise, and here the conclusion is A. All right, if you've got that, I'll draw up the truth table. For a second, I thought I was going to run out of space in the blackboard. And then I remembered that one of the premises and the conclusion are both individual elementary propositions. So we save some space. But especially in a case like that, you want to make sure you label your premises and your conclusions so you don't start looking in the wrong place for what you want to do. All right. There's your conclusion. Here's a premise, and here's a premise. Now, it's not going to kill anybody to work out all the rows of this truth table, and then having worked them out to see what are we looking for with validity. We want to see whether there are any rows in which all the premises are true, yet the conclusion is false. It can be done. It's not a life's work. Nevertheless, it gets tiresome. And so we're using the partial truth table now so that we can do just a part of it. Okay. Hence the word partial. For starters, you see, and this is before we work out even a single truth value, but for starters, you say to yourself, well, gosh, I only care about the possibility that A is false, that the conclusion is false. The conclusion is A. I know I can ignore the whole top half of the truth table, right? Doesn't matter what goes on up here. All that matters is that the conclusion is false, if it is, when at least when all the premises are true. Okay. And again, because one of the premises is itself a single letter proposition, that is to say B, right? We're not going to care about the bottom two rows of this truth table because B is false. If B is false, then we can't have all the premises be true. Therefore, we're not going to worry about finding a counterexample in those rows, a counterexample in which all the premises are true, yet the conclusion is false. Okay, so we only have rows 5 and 6 of this truth table to look at. Where do we begin? I suggest we look at the premise, if C, then A and C. Okay. It's a simpler conditional, and we can probably narrow down what we're doing still more. If C, then A and C. Now here, C is false, and where the antecedent of the conditional is false, you know the whole conditional is going to be true. Okay, so now, because we've got the premise B and we've got this premise, there might be a counterexample there with all true premises and a false conclusion. Let's wait and see. What about when C is true? Okay, then if C, then A and C, but A is false, therefore A and C is false, therefore this premise is false. That means, okay, you have to be careful. It's very easy to slip into an error right here and to think of the falsity of the premise as the problem. No, okay? The truth of the premise is the problem if you're going to have a false conclusion. So it's really only row 6, the antepenultimate row, in which we stand a chance of having all true premises and a false conclusion. For we do have a false conclusion there, and we've got these true premises. Now, so the only cynical way of putting this is the following. There's only one column, there's only one premise of this argument that's any bit of a headache to work out the truth values for. And normally you'd look at this whole truth table and you think I have to do that 8 different times. Instead, thanks to the partial truth table, we've got it down to but once. Okay. This is a conditional statement whose antecedent is itself a conditional statement. And you're about to gird your loins then and say, well, now I've got to work out if not A, then B. Watch out. Because what do we know about this row of the truth table? C, the elementary proposition C, is false. And what, sorry, I was about to cut corners and I see that I cannot cut corners. My error. So C is false. So what do we want here? We're looking for the possibility that the whole conditional is true. So for it to be true, the antecedent has to be false. For if the antecedent is true and then C, its consequent, turns out to be false, okay, then we have a false premise, okay? So we need that antecedent to be false. If not A, then B, okay? If not A, A is false, so not A is true. B is true, so that's a true antecedent. And C is false, so this premise is false. That means we don't have a single row of the truth table in which all the premises are true, yet the conclusion is false, which is to say, just a shorter way of saying the same thing, this argument has no counterexamples, which is to say, more briefly yet, the argument is valid. Hello. I want to close this session with one more example of the search for mutual implication. We're going to be looking at just two arguments, asking about their validity, but both of these are arguments with a single premise and then a conclusion. Indeed, they are two arguments in which the premise of one becomes the conclusion of the next, and the premise of the other becomes the conclusion of that one. We don't need to make a big mystery out of this. This is one of those cases where if you render these logical statements into a natural language equivalent, you can get an intuitive sense of how they're related to one another. So for example, you might say, it's not the case that if you're left-handed, then you're good at music. You're left-handed and you're not good at music. Sounds like it's saying the same thing, right? It's not the case that if one, then the other. And how do you assert, let alone show, that it's not the case that if one, then the other? You say, well, because you could be left-handed and not good at music, okay, right? These are indeed equivalent statements, but let's show them to imply one another, which is what equivalence ultimately means. Oh, that's a simple 4-line truth table, okay? I hope that's coming across. There we go. Here, and again, as I was saying at the beginning of this lecture, negations can be so hard to process. Negations can be hard to process. I try to set up a separate column when I've got a negation just to avoid error. Okay, so we're taking the conjunction of these two columns. That's a false. That's a true. That's a false. That's a false. Now, space did not permit a whole other column for the simple if A then B. But remember, you've got the truth table definition of if A then B just rattling around in your head all the time now. TFTT, right? It's only false one time. It's only false when you've got a true antecedent and a false consequent. Okay, TFTT. So just negate it. How do you negate TFTT? You go FTFF. All right. These are equivalent. Look at the columns, FTFF. Where the first assertion is true, the second assertion is true. Where the second one is true, the first one is true, like that. And so this is an extreme case of implication. That is to say, it's a case in which you can demonstrate mutual implication. If you wanted to see whether this implies this, you'd say, well, when this is the premise and it's true, does this ever come out false? No. When this is the premise and it's true, does this ever come out false? No. Indeed, each of them is true only once. When it's true, the other one is true. They imply one another. That's mutual implication. That's equivalence. And that's one of the identities that we're going to get comfortable with as we continue. I want to remind you of one last thing before we say goodbye to the truth tables, because this is really the last time we're using the truth tables. We might mention them, we might reflect on what they mean, but we're only going to be using the truth tables now, and then we'll say goodbye to them. Emil Post, that graduate of and instructor at CUNY, was able to show 100 years ago that truth functional logic is sound, that it is indeed, it is complete. He could only show that because he was able to define validity and equivalence on a truth table. So he had one standard notation in which he could give a concrete, absolute, exceptionless, unambiguous definition of validity. You can't do that once the logic gets more complex. In fact, just a spoiler alert, once Post proved what he proved about truth functional logic, he began to wonder, well, what about other kinds of logic? What about, and by this time Bertrand Russell and Whitehead had already produced their Principia Mathematica, and Post could ask, well, suppose you've got a quantifier. Is that kind of logic also going to be complete and sound? Suppose you've got two quantifiers, that is, a quantifier inside another quantifier, which, as we saw from, I'm really getting ahead of ourselves now, but this is just for us. Once you've got two quantifiers, nested quantifiers, which, as we learn from Russell and Whitehead in one way, we learn in another way from the work of Gottlob Frege, you have to have that kind of structure in order to define the functions of arithmetic. Okay, so you have to have that much structure for logic to purport to do the interesting things that people like Bertrand Russell thought logic could do. Then, Post asked, then is the system of logic still going to be sound? Is it still going to be complete? We're familiar with the answer to that question as it was proved a decade later in 1931 by Kurt Gödel. But Emil Post was asking the question. He had a different approach to it. Did not get it out in print. Some people would say he anticipated Gödel, even if he didn't have the complete proof. But he anticipated Gödel and his discussion of the completeness or incompleteness of more complex logical systems. That question quite aside, however, what's not in any doubt is that Post came first in actually demonstrating any logical system to be sound and complete. He demonstrated logically what people thought they could only talk about in a vague way concerning logic. And he did it using these truth tables. Thank you all. Goodbye.